All right. So this will be the last lecture before, well, Thursday. Thursday's the last lecture. Thursday I'll do mostly a course review. I certainly will be covering thermodynamics in Thursday's lecture because that's going to be on the final. That's part of the thing we need to review. I'm going to try and get through the rest of the primary stuff I want you to know about thermodynamics in today's lecture. We'll see if I make it out. My goal is to get to entropy. Actually, I think I'll probably start off with entropy, but not just to tell you what the definitions are, but to actually tell you how to calculate it, what it means, what the significance of it is, to the extent that I can in an hour and a half, and then tell you how to think about it in the context of PV diagrams, ideal gas, expanding and contracting, heat being exchanged, and what it means to say that entropy always goes up. Second law of thermodynamics, right? The second law of thermodynamics is that the change in the entropy, S is just entropy, the capital S with the series sign. The change in entropy for the universe, as long as it's bigger than or equal to 0, in fact, it's always bigger than 0, you can't get equal to. You can, at some limit, get it to be equal to 0. If things change in exactly the right way, or if they don't change at all. But most anything that happens in the real world results in increase in entropy. But that doesn't mean that the entropy of individual objects can't go down, right? Otherwise, there'd be no structure created ever. You wouldn't be able to cool off your whatever it is, the Kool-Aid you got in your refrigerator. You couldn't cool it off. That's lowering its entropy when you do that, right? You wouldn't be able to do that. So, second law of thermo, right? So second law of thermo. So I want to talk about that, and I want to talk about the concept of things we can actually calculate. Like what am I going to expect you to know what to do? I know what to do. I'm going to expect you to do some entropy type calculations on the final, perhaps. I don't know how I've written yet, but in past years you'll see examples. Oh yes, there are several practice final, like 4 up on V-Space, and I've now posted the solution steps as well. Don't look at them until you're ready, but you got them there as a resource after you're comfortable to take the exam at home and test yourself. So entropy, second law, and the notion of reversibility. Is it ability or ability? Reverse. I think that's right. Is that right? Yeah, I'll stick with it. This looks like anyway, there, it's a little better. Okay, reversibility. Super. So right off the bat, I'm going to do a demo before we get into equations and big ideas to talk about. There's some big ideas here too. To talk about the motion of air molecules in a room and what we mean when we say that there's some thermal energy. So can I get the camera up there? Can you see it? I think it's all plugged in. You should be able to hook it up to the. No, I mean, can you? So there's a feed from the. Oh, there it is. So what you're looking at there looks like some sort of Christmas display, but in fact, what you are seeing is a red laser bouncing light off of a bunch of smoke particles. So what we did before class is we lit a match, produced a bunch of smoke. What is smoke? Smoke is just a bunch of little soot particles, mostly carbon, but some other stuff mixed in, right? And it's floating around in the air. And the particles are very large compared to molecules of air. Large enough you can see them. You can see smoke, right? You can't see the air molecules in the room. Too small for wavelengths of visible light. You're shocked to hear. But you can see the smoke. So one reason we use smoke is it's big enough to be seen. There's a second reason we use it, and that is, and what do I mean by use it? We're using it to visualize the motion of air in the room. So there's two things you notice, right? After you realize that it's red because of the red laser, okay, fine. You can count the redness. Those little dots are the smoke particles. They're drifting downward mostly. That's because of gravity. They're just falling under gravity. But they reach terminal velocity a lot faster than we do. If you jump out of an airplane with a parachute, I hope, you wind up reaching terminal velocity like around, I don't know, 150 miles an hour. Depends on the exact shape of your body and everything. But these things reach it much more quickly. They're going very slow as they fall. But in addition to falling downward, mostly, in addition to drifting, they're also dancing around in random directions. And that's, of course, because they're being kicked by air molecules in random directions. The fact that the smoke molecules are large compared to the air molecules means that it takes a whole bunch of coincidental events to actually kick the smoke particle. A bunch of air has to hit on one side, a bunch of O2 and N2 molecules hit on one side of the particle compared to the other side, in order for it to have an appreciable effect on to accelerate the smoke particle. So that means that you see this random dancing is happening. Well, the particle's moving very slowly. It's very massive. And you're only seeing occasional changes in direction compared to what you'd see if the smoke particle were only as massive as an individual air molecule. In other words, we're using gigantic particles compared to the air to visualize the motion of the air, but not so giant, not as big as my body, for example. Like you don't see me dancing around because the air's hitting me. It's just because I'm not that guy, right? But up there, it's actually due to physical collisions with the air. And when Brownian motions is called, right? Brown saw this under a microscope. He said, I see life under the microscope. There's movement. But he didn't realize what he was seeing wasn't life. It was pollen molecules, pollen particles. That's why, not molecules, particles. That's why he thought they were alive and moving. In fact, he was just seeing this kind of thermal motion. And Einstein looked at this and said, for his PhD thesis, Einstein said, I see. What's really happening is that these molecules, the little molecules, they're too small to see, and they're too fast. They're too fast and too small to be seen. They are colliding with these larger things, causing them to dance around in random directions. And based on that, Einstein calculated Avogadro's number. He figured out how many air molecules there are in a fixed volume of air, and he got it within an order of magnitude. I think he got it within a factor of 2, in fact, I'm not sure. But he got it within an order of magnitude just based on the motion you see. So it's a nice way for us to visualize what's going on with air, even though air in the room is moving too quickly, individual molecules, and they're too small. And this demo is sort of an annoying demo over here. I'll do it really quickly, and then we'll get on to other things. I say it's annoying, it's loud. So I've got here is I got a little plate that shakes with ball bearings on it, and I've got a big thing. That big circle there is the big piece of metal that represents our smoke particle, and then the little ball bearings are like N2 and O2 in the air. So if I turn this around, it's annoying, it makes a loud noise. So I'll turn it on, and we'll see what happens. You'll see that the big guy moves a little bit, he dances around a little bit. That's like the smoke molecules up there, even though the little ones are jumping around a lot, really fast, and they're too small to be seen. Its wavelength of light were longer than the ball bearings. Let's see if I can get it to go. If I turn it up, it's going to get noisy. Come on. Okay. Oh, yes. There's the annoying level. There it goes. So the air's moving around really quick, but if you just focus on the smoke particle, right, you see them dancing in random directions, but it takes a lot of collisions, right? It takes a lot of collisions with the air before you actually see appreciable movement of this smoke particle. Anyway, you get the idea. That's all we're doing when we're looking at these things. Okay, good. So it's true. I'm not lying to you. There's thermal energy in the room. The air is not at absolute zero. It's at 300 Kelvin or so. And the result is that individual molecules have kinetic energy, an average kinetic energy that's proportional, represented by the temperature in the room, right? Temperature is just proportional to the average kinetic energy. But the direction of the molecules is random. So suppose we had all that kinetic energy for this piece of chalk. We took the kinetic energy of all the air molecules in the room and gave it this piece of chalk. In other words, I threw the piece of chalk in some particular direction at a velocity, so that 1/2 mv squared of the chalk, right, equal the sum of all the 1/2 mv squared of all the particles in the room. That'd be a pretty useful. Would be useful if I crashed into the wall and some damage. We could do a lot of damage actually. If I do it that, I could do it that fast, right? Given the size of the room and everything else. But if we had, that's a form of mechanical energy that can be usefully converted into other forms of, fully converted into work. You have something that's moving, and it's not, the motion is unified. All the molecules inside this piece of chalk are moving that way at some great velocity, right? We'll ignore the fact that it's at room temperature as well. We'll just say that it's out in space somewhere and the chalk is super cold, so that all the motions of the molecules are just given by, they're the same as the motion of the center mass of the chalk. In that case, all that kinetic energy could be used to do some useful work. It could compress a spring, right? We come in and compress a spring, and then you could put a little latch up, and then you compress a spring, and you've got, I forget the expression, 1/2 k delta x squared, right, of potential energy stored in the spring that came from that kinetic energy. Now you can't do that with your molecules in a room. Maxwell, one of the early physicists who worked these things out, whose name also goes on the distribution of velocities there, Maxwell's distribution of velocities. Maxwell's demon, named after him, is a fictitious sort of an object that physicists think about sort of as a convenient way to think about sort of Vedanta experiments or thought experiments about how to convert different types of energy into other kinds of energy. If you had a box with a bunch of particles moving around like this room with air molecules, and you have a little ratchet here that lifts a weight against gravity, you could set it up maybe in principle so that some little demon would decide, okay, let's let that air molecule that's coming in at the right speed and velocity, let's let it hit our spring or hit our ratchet or whatever it is that's converting motion into mechanical work and lifting some weight against gravity. But then when things are going the other way, don't let that happen. Another thing you can do is you can separate gas and you can compress the gas just by opening a little hole. And you have some container, right? And say, oh, I'd like to have all gas molecules on this side, but on that side, I don't have any work. I don't actually push the plunger closed. Let them just go through by chance. When this guy's heading to the hole, open up the door, let him go through, and then close the door when there's a guy coming the other way so he can't go through. That's Maxwell's demon would do that. That's more canonical, so the traditional Maxwell's demon. Turns out that there's limitations. You can't just do that. You can't just. It turns out the information you need to figure out where these things over are, or the measurement you need to do. When you think it through really carefully, it turns out the second law of thermodynamics is always true. You can't get useful work just because there's energy in the room. Another way to say it is, suppose I told you, well, I'm going to charge you $100 for two kinds of energy. Either you could have all the air in the room that's got some thermal energy. Maybe it equals, let's say we calculated how many kilojoules of energy there is in the kinetic energy of the gas in the room, or I'll give you the same amount of energy in the form of some coal or some gas, gas meaning petroleum gas, or maybe in a room that's much hotter, that's at 10,000 degrees Kelvin. Which of those is more useful as an energy source to actually do useful work? Well, the chemical energy in the coal and actually the really hot room, the room that's at 10,000 degrees with the same, we'd have to have many fewer numbers of molecules in this room to have the same amount of energy total, right? But each one would be moving faster, right? The temperature would be greater, right? Energy, what's energy? So let's take two ideal gases at different temperatures. Energy is what? 3 for monatomic ideal gas. We'll assume it's monatomic. 3 times nkt. Well, if I have a bigger temperature, I need a smaller number of particles to agree to have the same amount of energy. So if I have two boxes, one is really big, it's at room temperature, another one that's really small, but it's really hot. Well, that small hot one is much more useful. It's worth a lot more money. It's worth paying a lot of money for that as an energy source. It's not worth paying a dime for the energy in the thermal energy in the room, the gas molecules in the room, because you couldn't use it to drive a heat engine to actually get useful work out, even though it's the same amount of energy, right? In other words, energy is conserved as it goes from one place to another, as you convert it from one kind to another kind of energy. But over time, because of the second law of thermodynamics, and things we'll discuss in more detail as we go here, so we give you a heads up for all these things, what happens is the quality of the energy goes down for any realistic process in the real world. You can do less useful work with it, even though all the energy is still there. It's conserved, right? That's why there's energy crisis. Well, there isn't a crisis now, I guess, but that's why we periodically have energy crises. That's why we pay a lot of money. That's why it's important for the U.S. to think about where we get our energy and what we do with our energy. Because even though energy is conserved, high quality energy is not. The universe is constantly losing high quality sources of energy. Hot places are cooling off and cool places are warming up. More the former than the latter. But both those things occur because of heat flow. And the result is after a while, it'll be like the air in this room. Everything will be the same temperature and you won't get heat flows anymore. And that's the heat death of the universe. Anyway, so lots of high-minded concepts. Heat death, you don't worry, it's not going to happen tomorrow. But we think it's going to happen someday. But it could be when I say we, physicists. But there's a lot of open questions about evolution of the universe and exactly what form energy is right now in the universe. A lot of interesting questions about dark energy, dark matter, everything. Beyond scope, of course. But anyway, so there you have it. So that's a very high-minded, woolly discussion. So let's get more specific and think about these things. How do you calculate entropy? What does it really mean? I told you how to calculate energy, right? You can calculate another way too, right? Given that PV equals nkt. Oh, this is all. Yeah, this right here is for a monatomic ideal gas. So these are not true for any system. It's true for an ideal gas. PV equals nkt. In fact, this is true even for the monatomic. It's still an ideal gas approximation we use to get that expression, right? And so using that, I can replace the nkt with PV. So I can do this, right? Okay. So we've got these expressions. What else do we have? We have the second law. Excuse me. The first law. Okay. This is all just to recap. First law is the change in the energy, right, is equal to the work you do on the system plus the heat you add to the system. So heat in plus work on, both positive if you write those subscripts like that. What else? What else should I put up there before I launch into specific examples? Well, how about entropy? So here's the thing. I've asserted this in the past, and I'll assert it again now. There are state variables, and there are these other things that are not state variables. What is a state variable? State variables are variables that, if I know the macroscopic properties of the system, I know the pressure, the volume, the number of particles, right? I can calculate the energy, right? There's energy as a function of temperature, number of particles. So energy is a state variable, just like P is, just like V is, just like the number of particles, just like the temperature. Yes, energy also is a state variable. Okay? So is entropy. Entropy is a state variable, even though it seems different than the others. It turns out it's a state variable. I'll talk about why it seems different in a minute. There are some other variables that are very important for us that are not state variables. So not state variables. These are something else, right? This includes stuff like the work and the heat. And I'm not saying subscripts. It doesn't matter if I write work on or work by or work on. Neither of those are state variables. There's different conventions that negative each other. Same thing for heat. Heat is not a state variable. These are path-dependent quantities. When I calculate one of these, I have to know something about the history of the system. It doesn't make sense to say how much work is in the system right now when it's in some particular state. That doesn't mean anything. But I could ask, well, how much work did it take to get from point A to point B on a PV diagram along a particular path? I can say, how much heat had to be exchanged in the outside world? What was that work done? Now, entropy, we're going to calculate it with this expression I'm going to write down. I'll write it right here. Here's entropy. Well, if I want to know what the change in the entropy is along some route on the PV diagram, well, it's just going to be, let's see, just for myself, I say, oh yeah, if I want to know what the change is, sorry, Q is TdS, right? Oh yeah, and if it's Q in, good. So that means that ds is going to be, I'm going to write as an integral first, and then we'll see what happens when the temperature is constant. But it's going to go like dq in over t from point A to point B, whatever path you took. And if t is constant, you can say, oh, that's just going to be the total Q in over the temperature that the system is at that whole time. Okay? So what have I done here? I just asserted, like this is a definition for the change in the entropy. If you add some heat to a system, then the entropy goes up. If the temperature is big for the system you add the heat to, well, then the change in the entropy, did I do this right? Does that look right? I think it's right. If I add some heat to a system, and it's, yeah, this is correct. If I add some heat, I have to make sure my sign's right. If I add some heat to a system and it's hot, the change in the entropy is not very large because hot means T is big, so the denominator, the bigger T is, the smaller the change in the entropy. If I add heat to a cold system, though, the entropy changes a lot because T is very small, and that's really important. That tells us that when heat flows from hot things to cold things, the hot things lose a little bit of entropy, but the cold things gain a lot of entropy. In a nutshell, that's why entropy goes up in the universe. Whenever there's heat flow, it goes from hot things to cold things. Unless you've got a refrigerator and you're applying useful work from some other system. But whenever you have a closed system, two things interacting on their own, heat flows from hot things to cold things. And this formula tells us right away, oh, it's going to go in the direction where the hot thing cools off and loses a little bit of entropy. But the cold thing gains a lot of entropy when it gets a little bit of heat. That's why entropy goes up in the universe. There's another way to think about entropy that's related, but it doesn't seem obviously related at first. And that is that entropy reflects the number of states a system can be in, given all of its macroscopic variables. Given how much, in particular, given these are energetically accessible states. But it isn't just linear with that. It's actually, we write it as a log. So I'm writing ln in script here to represent the natural logarithm. It's the same thing as log subscript natural number e. Excuse me. Yeah, e is the letter for natural number e. So log of what? For the number of accessible states. Accessible, I'll let you spell it, but it's accessible states. Okay, these things seem different, but they actually are the same thing. This is the manifestation of that. And the thing about this formula is that the way we're actually going to calculate entropies most of the time is going to be using this formula. Saying that, well, we're going to look at the heat flow, and based on the heat flow, we're going to figure out what the change in the entropy is. And because we're doing a change equation sort of thing, people tend to think, oh yeah, entropy is this mysterious thing. It's hard to think about these other variables. And we're calculating it in terms of changes, when we do work and heat, Q and W. And you think, oh, so that means that maybe entropy isn't a state variable. It's only dependent. It depends on the path you take and all this stuff, but it's not true. The reason we don't have a formula like this in this class, so right here I got E equals 3 halves NKT. Well, there's another formula just like that for entropy, S equals, and it's just that the formula is big and complicated. And it doesn't show up in our textbook, even though the textbook does a lot of stuff beyond the level I want to do it in the thermodynamic sessions. Trying to get some guidance to my lecture a little bit about sort of the level I expect to understand it. The book doesn't include the formula for entropy, and no textbooks do. In fact, undergraduate textbooks tend not to do that. It's a complicated expression. So students sometimes get the wrong idea that somehow entropy is not a state variable, but it is. So if you're on a particular place on a PV diagram, the entropy is well defined. Doesn't matter what path you took to get there. If you're at some point down here, you know that, and you're told, the number of particles in the problem, or you have some side information about that. You know what P is, V is, the number of particles, and you know it's an ideal gas, right? Then you know its energy. You know that its entropy is well defined, even though I'm not going to write the nasty formula for it. It's a specific value. And you know what else? PV and T, I guess that's the state variables we've listed. But you don't know W or Q to get that. You have to know, well, W or Q for what? What path did you take to get there, right? And anyway, so there you have it. I said a lot of words. So let's look at some of those things we talked about last time. I'll jog your memory, and then I'll add a few more on the end. Some other processes we didn't talk about. So we talked about what happens if you go like this. Let's consider expansions for this. What's the same thing in reverse? If we went from here to here, it'd be the same thing. Right? We're going from V1 to V2. That's an expansion because V got bigger, but P didn't change, right? So in this case, was work performed on the gas or by the gas, or no work? What is it? On the gas, by the gas, or no work? Yeah, that's right. The gas expanded, so then work by, which is the opposite of work on, is positive. So that means the work on is negative, and it's equal to, just the area under the curve. It's just that. All right, so you guys remember that. It's just going to be P. In this case, I call it P1, but it's the same as P2 times delta V, right? And then we figured out, too, the change in energy. Did energy go up or down for the gas during that expansion? The energy of the gas. Or did it not change? Did the energy change? No? Did it go up or down? I'm hearing a little downs and ups. Let's ask this. Did the temperature go up or down? So this region up here, what is temperature? PV equals NKT. So that means T is PV over NK. NK is just a constant here, right? So T is proportional to P times V. When you go up here, it's hot. When you go down here, it's cold. The bigger P times V is, where do you get big values of P times V? Well, when P and V are both big, P times V is really big. So that's hot up here. That's cold down here, right? And if you want constant temperature, that means P goes like 1 over V, right? So constant temperature lines are like this. They're not straight lines, they're curves. They go like 1 over V, right? So that means that when you go from here to here, are you getting hotter or colder? You're getting hotter because the constant temperature is like that, right? And so you're up that way compared to where you were down there. So that's right. That means that the change in temperature was positive. The gas got hotter during this process, and therefore the energy went up or down. Because energy is just 3 halves times NKT. If T goes up, energy has to go up for an ideal gas. So there you have it. And we worked all those things out. What's easy about this case is it's constant P, and that means that the work is easy to calculate. It's just P times delta V. We worked out how to calculate the rest of those things. We said, oh yeah, Q in then just winds up at the first law of thermodynamics. It's just the change in the energy minus work on, which winds up being positive because you're subtracting a negative number. And then what did we wind up with? We wind up with, I think, 5 halves. When the dust clears, P times delta V, right? Because you got 3 halves from the energy part, and 3 halves from the this is 3. Sorry, you get 2 halves from this. Because 3 halves equal to 1 of P times delta V, and you get 3 halves P delta V from the change in energy. Right? The change in energy is just going to be, energy is just 3 halves PV, so it's just 3 halves P delta V. And it's positive. Delta V is positive, it got bigger, and sure enough, energy increased. Anyway, so okay, we did all that last time, but there it is again. If we wanted to know which way does the entropy go, so how then the entropy in this case is a little tricky because the temperature is changing as you move from here to here. Does everyone see that? Everywhere along this line, the temperature is changing a little bit. And that means that if we wanted to use that formula to calculate how much entropy change there was along that path, it'd be a little nasty because we have an integral, where inside the integral, like what is the integral? It's got a dq over t. Well, the t is a function of where you are along the path, function of v, say, and dq, anyway, it'd be complicated. So what we'll do instead is I'll just ask you, well, what's the sign of the entropy change? So right here, is the entropy going up or down? Who thinks up? Who thinks down? So just a few hands. I think one of you voted twice. Just a few. That's entropy in action. No, so there's only people who raise their hands. How many have no idea how to figure out what I'm asking about, how the entropy changes, about whether the sign's positive or negative? Okay, equal numbers. So most of you are not voting in that last. So let's see. Well, what's my definition for, or what have I written for entropy? My formula for change in entropy. This is the one. You can think about this, but this one's probably more easier for us to figure out. In this case, delta S. Well, everywhere along the line, if Q in is positive, if we're adding heat to the system, its entropy is going up, no matter what the temperature is. Because remember, this is absolute temperature. Absolute temperature is always positive. Right? This isn't Fahrenheit, this is Kelvin, right? So this could be 0. Okay, that could be infinite. Yeah, you can see what happens. If this were 0, the change in the entropy would be infinite just by adding a finite amount of heat. But this is never 0.